I can ask him. So if we share things seems fine with the here, but that's not seem online. It still show here's what online people see. Yep, that's right. Is that correct? That's it. Okay. This, oh, so is what they're supposed to see. Okay.
Yeah, so the way it's set here is it's on full screen mode. So you'll just have to, right now we're on the
Yeah.
main screen. So if you just slide over, there it is. But let's get this guy out of the way here. Yeah. And yep, so then it should be good from here. Oops, just click on it.
And if you go back to
Yeah, three fingers.
The other side.
Yep.
We just try again. Is
Sure. Sure.
I don't know why doesn't start from the beginning ever. So this will be then either way. Okay.
Was that the movie or is there an actual?
That's the movie.
Oh,
That's it.
perfect.
It was an animated GIF.
So no audio with it or
Yeah,
cool.
it's fine.
Awesome.
Okay. PowerPoint is
We actually,
yeah.
can we start check one more? There was one movie actually on the third slide.
Yeah.
Yep. Good. Okay. Great.
PowerPoint. I think it's good. Okay, this.
That's all right. Why did I lose it?
Sorry, I just noticed you were pulling up my slides. Is everything up?
Yeah. Yep, we're good. Is it showing up on?
No.
Oh, I think we're stop sharing here. That is why we stopped sharing. Okay. This is the first one? Okay. Okay.
Say this.
And we're currently sharing right now.
Okay. And we already share screen. Fine. Perfect. Okay.
Yep. So once you're ready, you can just slide over to the. Yep, right there. You do it just to hit right. That way you jump to the actual slide. after this section.
Exactly. I think the guys might be
Yeah,
remote.
we're gonna work it just so
This guy might
it's
be
a
remote.
little
Yes.
better. But
Thank you. Hey Thomas, can you try to grab the screen and share on your side?
Yeah, sure.
Remote.
Can people hear me okay in the room?
Yeah, we can hear you well.
Okay, good. Let's see. Sure, it's this one. Can people see that? I hope they can.
But I think it's our side, right?
We have a full flight today. If you guys could move quickly to your seats, stow your luggage and move out of the aisle, that will help us have an on-time departure. I'm going to speak on language we all understand.
Okay, go ahead, Thomas. I think we.
Okay, so I guess people can see the slides then.
Yes, we do see slides.
Yep. Great. So yeah, thanks for giving me the chance to talk about what the Fangs people have been up to for the last, I guess, almost a year and a half now. So the title at the top is, I think, the title that I submitted as the abstract. But just to kind of bury the lead, JWST, we've seen a bunch of high redshift stuff, but it's also really great for nearby galaxies. So this is really a talk on how we spent a year making the prettiest pictures that we could. And so just to quickly introduce the Fangs team, this is our team photo from our most recent team meeting in sunny Pasadena. These are at the Carnegie Observatory, so this was the day before the blizzards arrived in what people described to me as unprecedented Californian weather. So it's about 150 people kind of spread out across 6 continents. So lots of fun trying to organize telecons through various time zones, and a bunch of these people have been working hard on data reduction or actually science exploitation of the data that we've been getting. So to give a quick overview, this is a purely imaging proposal. It was a Cycle 1 treasury looking at 19 nearby galaxies, and this was in 8 filters, 4 of which are in NIRCam, 4 of which are in MIRI. It's about 100 hours total charge time, and the observations have spanned the entire operating run of JWST thus far. So we had our first observations come in before the embargo lifted on the early release science observations, and we're getting stuff in still now for the Cycle 2 stuff. So it's been an interesting test of time cadence as well as kind of coverage on the sky. So Janice Lee, who is at SDSCI now, is the PI, also co-PIs Karen Sandstrom, Adam Leroy, Eva Shinra, Dave Thilke, and Kirsten Larson. And so these galaxies were chosen because they have a bunch of great ancillary data. So they all have ALMA, MUSE, HSD, Astrosat, VLA, Meerkat, you name it. Essentially, these are some of the best studied galaxies in the universe. So it made sense that JWST should point at them as well. And the observations for Cycle 1 are now complete, barring 2 failed mosaic tiles where NIRCam didn't manage to get its guide star locked in, but the whoppers are in, and I think they're being observed as a little Christmas present to us. So beyond that, we also have a Cycle 2 treasury, which is another 55 galaxies and another 150 hours of observing time. So it is big data, and really the science objectives fall into 2 main categories. One is the earliest phase of star formation, which is looking at embedded clusters, mostly with NIRCam, but also with MIRI. The other is looking at the morphologies and properties of the dusty interstellar medium. So this is PAH, polycyclic aromatic hydrocarbon, and dust continuum emission, which mostly comes out in MIRI, but also comes out in NIRCam. And the thing is that these two different science topics have very fundamentally different requirements on the kind of data quality that we need. So really, we need good point source photometry for getting stellar clusters, which are mostly unresolved, even in the short wavelength NIRCam bands. But also, if you want to study the extended dust properties of these galaxies, you need good large-scale mosaicing, which means background levels and absolute flux levels. So these things have been problematic for us, and we've been working on them. So we've developed our own pipeline. I call it PJ Pipe, the FANG's JWST pipeline. So the official pipeline is excellent, but given our data volume and the fact that we've been having these regular observations coming in, we really want something that's mostly hands-off and can deliver science-ready mosaics fast with minimal intervention. So this essentially wraps around the JWST pipeline and has some bespoke but generalized routines, which should hopefully be of use to people. So the repo is on GitHub and is currently private, but if you want access now, please just ask, and we're hoping to have it public by the end of the year. There are still some issues that we're ironing out. But the good news is that we got one of our Cycle 2 observations down, and about 6 hours after it had beamed down from space, we had a mostly science-ready mosaic. So we're essentially there in kind of like real-time reduction. So I called this Lessons Learned from Cycle 1. I don't have time to go over all of these, so I will flash these up now. So if people want to take a quick screenshot and want to ask about things that I may skip over during the talk. I've also tried to highlight where these problems are more general and seem to be covered by other talks in the session. This may be wrong. This was just from eyeballing the abstract, so I'm sorry if I'm misrepresenting your talk, but hopefully these are reasonably accurate. So the first one is that if you're getting MIRI backgrounds, time is more important than position for them. So one of our very first observed galaxies was IC 5332, and the NIRCam observations failed, which is when we also get our MIRI backgrounds. So what we had been using was the closest backgrounds that we had in time, which was from NGC 7496, which was taken 3 hours either side of IC 5332, don't remember which way, but in a different part of the sky. And that's the one that you see on the right. So when we got the NIRCam observations reobserved about 8 months later, we had the ones that were close in position, and that's what happens if you use the one on the left. So clearly you get a better looking background when you're using the closer in time to closer in position ones, and actually if you combine them, things get worse. So if you have observations that fail in this way, the recommendation I would give is request that you get everything reobserved, the science and the backgrounds. Number 2 on the MIRI side is that the coronagraph is its own beast, and I think Michaela might have touched on this a little bit in their talk just before the break in creating these superflats, but actually the background level in the coronagraph, which is this kind of small square you see up to the top right here, is different to the level that you see in the main science chip. And so we hack our way around this by essentially masking out the science data from the main chip in one file and then from the coronagraph in another file, and treating them as different observations, which means that you can background match between the two things. So this may be improved with future calibration files, but as of now, if you just let the pipeline do its own thing and you have a mosaic where the coronagraph overlaps the main science chip, you will see the coronagraph very clearly in your final mosaic. Lesson number 3, astrometry is hard. And it's especially hard when you're doing mosaics because the guide stars often have not to the level that you require them absolute astrometry. It reflects the uncertainty in the guide star catalog, and this should probably get better with time. But what we're finding is that lots of things that are flagged as guide stars in our observations are actually things like H2 regions within our own galaxy. So they're actually extended, which means that centroiding them at the JWST resolution is impossible, so you get shifts, sometimes of kind of half an arc second or more. I've seen quite large shifts, and that reflects this uncertainty as the guide star catalog improves, as kind of observations are going to go on. Of course, matching astrometry between tiles in the mosaics is also difficult when the tiles have no point sources, which is really a problem for our long wavelength observations. The 21 micron MIRI observations essentially have no point sources at all, so locking things is difficult. It's also a problem when you have too many point sources, we're discovering. So the F200 is absolutely full of stars, and finding which ones to lock onto for the astrometric solutions is also tricky. So what we do is, because we have kind of these cycling dithers between filters, we just use the optimum filter in the NearCam and the MIRI band. So in our case, we use the F300M, which is mostly stellar dominated with a little bit of dust, and then the F1000W, which is mostly stellar dominated but with a bit more dust than the F300M. And then we just apply those solutions to every other band. And it seems to work pretty well to within about a pixel at the worst. And a lot of them are kind of sub-pixel. The NearCam basically locks on almost perfectly. The MIRI is a little bit more spotty, but work is ongoing. Next up, background matching. So as far as I understand it, and always happy to be wrong, is that the way SkyMatch works in the pipeline at the moment is it uses kind of a sigma clip in overlap regions, and the assumption that in the rest of the chip there is some true background that you can measure somewhere, which is not true for us. Our observations are completely full of emission all of the time. So instead what we do is we essentially copied what Montage does, where for all of the overlapping regions we get the difference between things on a pixel by pixel level, get deltas between each tile in that way, and then find a global best fit minimum to subtract from each tile. It works a little bit better for NearCam just because there is a bit of gap between kind of stars and things. And also I think because just the noise level in the NearCam is lower than it is in the MIRI, it works significantly better for the MIRI. So this is, on the right, is just a difference image between the mosaic that you would download from MAST and the one that we've reprocessed. So you can see that there are differences of kind of up to half a megajansky per steradian or more. And it gets to be more problematic as you get to the longer wavelengths as well. Returning to astrometry, lesson 7 is that it's also hard to lock to an absolute reference frame. Our observations have very few Gaia sources, and most of the Gaia sources are actually H2 regions within our galaxies, which is a problem because they're resolved at the resolution of JWST. So I'll do what we call self-calibration to annoy radio astronomers, which is that because we have HST imaging for all of these galaxies, we use vetted AGB sources from within the galaxy. So these are true point sources and are actually within the field of view of our observations, which we can use to get absolute astrometric solutions. Again, for MIRI, we inherit the solutions from their F1000 band, which is the one with the most point sources, although there may be some hope in using the very reddest sources at the longest wavelengths, although there are very few of them in the galaxy, so it may be quite tricky to lock on properly. And this works well. The residual shifts we're seeing from kind of filter to filter and also between the HST is now significantly less than 1 pixel. And I think a lot of that residual shift that we're seeing is actually due to rotation. Currently we're just fitting a shift, but adding in a rotation now that we're better locked on may improve this solution. Like we're seeing, shifts across the mosaic essentially, which is probably hopefully rotation. The next lesson is that fluxes are tricky when you're subtracting what you think is a background but is actually the galaxy. Our observations don't really have backgrounds in them, so when we do the background matching and subtraction, it's subtracting off real flux. So instead, what we do is we degrade all of our JWST images to comparable wavelength-ish Spitzer and Wise images and just fit for a DC offset once we've got our final mosaics, and we can fit for an offset between filters as well, assuming some kind of color correction. And this seems to get our fluxes good to about the 0.1 megajansky per steradian level, but there is some scatter. The scatter is worse at the Miri levels, and I wonder if this is what the Sears folk are also seeing, that perhaps it's something to do with the calibration files that perhaps need some improvements, but unclear. It's also that we don't really have particularly close filters to anchor to, so that may be causing some issues, that there's actually color gradients across the galaxy. But it's not all doom and gloom. Thankfully, it feels like we're almost there. We're planning to have our big data release of the 19 galaxies by the end of the year. Fingers crossed. We'll see how that goes. We're still improving our pipeline, and the official pipeline is also still improving, and the reference files are still improving. So sometimes, you hit go and you actually get something that looks drastically better. With me having done no work, but other people having done lots of work, which sounds great to me. The good news is that we essentially now just add the name of a galaxy to a config file. We hit go and we have mosaics of 8 filters in a few hours, which is cool. It's big data challenges, but big data solutions. And it's not all doom and gloom. The pictures are stunning. So this is from the survey paper from JWST, put out kind of end of last year, of our first 4 galaxies. And on the left you have the Spitzer images, and on the right you have the JWST images at comparable wavelengths, and you can see that really it's a game changer, both in terms of resolution and the sensitivity that you're getting. It's really like kind of wiping the sand out from your eyes, that you're seeing the embedded young clusters and the dust filamentary network that you have going on in these galaxies in a completely different way. It's really a game changer. So I think that's about my time up. To conclude, JWST is great. The JWST pipeline is great. Observing things with JWST when emission fills the field of view is tricky, but it is doable. Things like 1/f striping subtraction has been an interesting challenge in particular. And we have this pipeline that is mostly automated. When the pipeline goes public, we'll also be providing all of our configuration files so people can see how things are set up and re-reduce the data as they would like. So we're giving config files for a number of projects, and that will be public very soon. So I will finish there, and if people have questions, I don't know if we have time, but I'm sure the Slack has stuff going on. So thank you.
Excellent. Thank you very much. We do have a couple minutes for questions. One of them from the Slack, could you give us a sense of the compute power that you need to process your data sets? And
so it's running over here at the moment. It's on a compute node with 500 gigabytes of RAM, which is overkill actually for what we need. The biggest RAM usage ends up being the outlier detection step in level 3. And it's only really a problem for the short wavelength near cam mosaics, where it kind of uses maybe a couple of 100 gigabytes of RAM, even through all like the parallelism and stuff.
Perfect. Okay, yeah, and please do give that answer in Slack as well. We're just having a little bit of human interaction here instead of it all being Slack. Let's see. So the next speaker is here in person, despite what my notes say. Awesome. Marco's gonna set up. Ooh.
Great. Hello, good morning. Thank you to the organizers for having me.
Can you just check if the light is green?
It is red.
Yeah, that's not. Button down. We in this building are trained to hear the difference between the mic there.
Perfect. Thank you. My name is Ben Johnson. I'm going to be talking about NearCam data taken as part of the JADES GTO program and some aspects of that data that have proven challenging for calibration and reduction. So just to orient you, I'm also going to describe a little bit about the WST calibration program that was accepted in cycle 2. The JADES program is a combination of GTO time from the NearCam, NearSpec, and MIRI teams, constituting over 800 hours of mission time. There are image examples. It's targeting good south and goods north. And there are image examples in 10 filters, usually including many small-scale dithers, and covering about 160 square arc minutes. To date, we've collected greater than 10,000 individual SCA images in goods south and 4,000 in goods north. And the GEMS, Fresco, and the Cycle 2 program, 3215, have added a number of different filters in this same area. We've had 2 public data releases of Good South data, one in June and another just recently with some more of our year 1 Good South data. The NearCam imaging in JADES has been used to select targets for NearSpec, notably the highest redshift spectroscopically confirmed galaxy to date. Numerous papers have been based on the JADES data. The JADES team has had 10 accepted papers and 26 submitted, and the DR1 data from June has been used in about 10 papers by the community. We've visually inspected every JADES, GEMS, Fresco, and 3215 image taken at several stages of reductions. And we typically do that using these GIFs that step through different exposures in the dither sequence. This is extremely helpful for separating between detector artifacts and transient artifacts and on-sky sources. So here you're seeing on the left the rate image. The second image from the left is the stage 2 cal image. Then after our WSP and background subtraction, and then the masking that we apply is shown in purple on the right. And you can see the WSPs in the top middle here. And then in exposure 6 of this dither sequence, there's a snowball that strikes and persists for the rest of the dither sequence. Everything I'm going to say is right now based on pipeline version 1.11.4 with 1130 PMAP, unless so now I'm going to transition a bit to some of the issues that we've been finding difficult to address and talk a little bit about what we have tried. So the first issue is snowballs. So the regions impacted by snowballs are typically left by higher or lower values than their surroundings, and we wonder if this might be caused by a bias in fitting the shortened ramps after a jump detection. In mosaics, this isn't too much of a problem because when you're combining many exposures together, they get averaged out and the uncertainties are larger for these, but it does reduce the effective exposure time. And it also impacts forward modeling of the data at the exposure level. There are many snowball correction parameters, so there may be some that could mitigate this, and I would love to learn them. It can be difficult to optimize over them. So another issue that we've encountered, as many others have, we've heard this morning, is one over F noise. So we're using software to simultaneously fit the rows and the column 1 over F noise. So this model that we use has 5 times 2048 parameters plus 4 offset values for each amplifier. So we're modeling it as an additive offset separately for the rows and the columns. This is approximate and can cause biases near large, bright objects. So going back and masking those objects beforehand, we try to do that a little bit, but that can be improved. And one issue that's arisen recently is that in about 3% of frames, usually on detector A1, it looks like the current snowball algorithm with largely default parameter sets is identifying 1/f noise excursions of snowballs. We think that's what's going on. But we see the stuff like this in the rates where you have these linear features. Where we have these linear features that appear blobby, and the snowball rate is extremely high as reported in the header. And this is new behavior in JWST 1.11. We didn't see this in 1.10. Another issue that has come up is persistence. Our first observations, actually, of Good South were taken right after the trapezium cluster. And so this is showing the persistence pattern of the Orion Nebular Cloud. That data resulted in, the trapezium data resulted in a Nature paper, so good. But it was scary when we first encountered this. So the top exposure is showing the first exposure after trapezium, and then the bottom exposure is showing the end of the dither sequence, actually the exposure in the next dither sequence, in the next filter, 3.5 hours later, and you can still see it. This decays inhomogeneously depending on pixels, and you can see traces of it up to 10 hours later. And it's not just trapezium. Other high background observations have caused noticeable persistence in our data, such as low ecliptic latitude F150W2, so the wide filter gets you higher background levels in terms of counts, and that can cause persistence to bleed into our observations as well. It does mean that there is a potential to use these kind of uniform background sources to construct a data-driven model of persistence and maybe recover some of this data. Other persistence issues, so beyond the background, we occasionally see persistence from bright stars in previous programs. So NIRCam is always open to the sky, and so we do also see dithers and slews. So that's what you're seeing here on the left. This is not stepping through. There we go. So this means that bright fields or high backgrounds can cause NIRCam persistence even if other instruments were active and NIRCam was not actively taking data, so that'll make it a little bit difficult to use previous observations as models for persistence. Other persistence effects that we've seen, wavefront sensing, so a lot of our observations would come after wavefront sensing observations, and you can see in the top left corner an imprint of the wavefront sensing star. This is in the same location all the time, so it's easy to identify, and presumably this will become a very well-characterized part of the detector, the persistence here. And so that could be mitigated in that way. Right now we're masking pixels. That's what we tend to do for these kinds of features. And then, as mentioned previously, snowballs, the cores of snowballs can persist into later exposures, and these can show up as hot pixels and mosaics. And so I was interested to hear James talk earlier about tracking this across exposures, and that's something that we're looking to implement. Great. WISPs. So WISPs appear in a number of the NIRCam SW detectors. This is the WISP template that we're using. We constructed our own WISP templates for each SW detector and band based on stacks of the calibrated frames. After doing a source masking based on the LW mosaics, right? So we have very deep mosaics. In LW, we use those to mask, and then we generate a stack of the unmasked pixels to find WISPs. The WISP morphology is wavelength dependent, so here's F150W, F200, and you can see them stretch out and move around. And so this is a little bit difficult to do for bands that do not have many examples of images, especially because it does seem like the WISP morphology may also be time or pointing location dependent. And this wavelength dependence means that they may also change with the morphology of the SED of the offending source or whatever light is making it. One thing that has helped a lot in disentangling these WISPs, or to constructing these templates, is the new flats, which improved things a lot, and also the restricting ourselves to images that do not have persistence in them, because it's very hard to disentangle those. And constructing more flexible WISP templates and also sky flats is the goal of the Cycle 2 calibration proposal 3905. So as I mentioned, the WISP templates may be more than one parameter family. In addition to changing with wavelength, they appear to move slightly depending on time or pointing. The 3905 program is going to construct and release WISP template library while quantifying this behavior as a function of time and position. So here I'm just showing on the bottom an example where we've got a science frame on the left, the template in the middle that we constructed, and removing the template from the calibrated science frame leaves a small residual because the WISPs moved a little bit. So how are we going to go about this? The plan is to reduce all suitable images with a common pipeline version, and we're well on our way with that. And using the deepest possible LW mosaics for all of this data. We'll probably restrict ourselves to data that is, is part of a deep observation or a deep mosaic. To detect and mask galaxies and stars whose going faint really helps there for those masks. And then using just the source-free pixels in a given SDA and filter, you can construct this WISP template issue as a matrix operation where you've got a number of WISP templates, not just a single one, but some linear combination of WISP templates that's producing the background. And so we're going to explore various matrix decomposition techniques, including non-negative matrix factorization, to find the set of spatial templates whose linear combination explains these WISPs after source mask. Great. So when there are not enough distinct images to adequately sample every pixel, so this happens especially when if there's going to be a lot of time variability in these WISPs, we're going to look at using the covariance information from the WISP templates that we do have in order to impute WISP values where there's missing data, right? So if you've got the structure of these WISPs imprinted in a covariance matrix, pixel covariance matrix, spatially dependent pixel matrix, and you can use that to impute WISP values and uncertainties on those values in places where where the galaxies have covered up the WISPs and you're not quite sure what the flux is. Okay, so now I'll transition to astrometric alignment. This is mostly, in our estimation, solved to the level that we need it to be solved. So the astrometric stability of JWST is fantastic. And then combined with the quality of the near-cam distortion maps, we've implemented a scheme where we only compute a single tweak for every visit, right? So we use the F115, F150, or F200W exposures to get an astrometric offset from a reference catalog. Thank you, Gabe. And then we apply that tweak to every single exposure in that visit. And this works extremely well. And it allows us, it keeps us from imparting noise from this astrometric reference matching process into the individual bands. There does seem to be a 1:1 pixel offset between the LW and SW distortion maps, but I need to look into that a little bit more. We correct for that manually, and then we override a few missing distortion maps for a couple of SCA filter combinations in CRDS. Nearly all Gaia stars are saturated on our images. So over here on the left, I'm showing a set of 18 out of the 30 or so Gaia stars in our Good South imaging. On the left is showing the astrometric offsets that are computed. The second to the left is showing the data for one of the exposures. In the middle, I'm showing a WebPSF model. And in the right, I'm showing the residual. So we fit the outer portions of the Gaia stars. We fit the diffraction spikes effectively to get centroids for these stars in every single exposure in our data. And the stability looks very good, and the absolute accuracy is also very nice. So just for fun, we did get data recently in 2023 as part of the 3215 program and in medium band filters. So here I'm showing RGB image with F277W taken in 2022 in green and F300M in 2023 in red. And there's a slight offset between the two. This is a brown dwarf at about 20 nanojanskis. The proper motion computed from Spitzer versus JWST was about 30 milliarcseconds a year, and indeed it's offset by about a pixel. That was fun. Another thing that happened is that we came back in October 2023 to the Good South field to finish proposal ID 1180. We basically did the very same, very similar jitter pattern, moved a little bit over to cover some of the gaps, and similar filters, same PA. And this allowed us to construct different images via simple subtraction. So we did no PSF convolution, no rescaling, and no extra alignment, and you get something like this when you subtract the 2022 data from the 2023 data. And this is nice as a test for astrometric alignment, also for flat fields, because we're moving the sources over a little bit, and for PSF stability, which seems quite good. So just to show that a little bit more. If you're in the front row, so there are some residuals that come from 1/10 or maybe 2/10 of a pixel offsets in the astrometry. There's also in the top right a transient. And so I'll just close with our priorities, future directions, what we are hoping most for and what we're planning to work on. So the snowball corrections that don't have these sort of positive and negative deviations would be great. Improved WIST templates, which we are working on. Persistence flagging across exposures, which it sounds like there are some existing implementations that we can adopt. And improved 1/F noise treatment. So what we've been doing is very approximate. And I'll close there. Thank you.
Awesome, thank you very much. We do have some questions. We'll just do a couple. The next speaker could maybe come get mic'd up while we do this. One question was, you should keep that. We have two, and I want you to entertain the crowd while we do that. Have you tried using galaxies as an astrometric anchor?
Yeah, in fact, sorry, the reference catalog that we use is mostly galaxies.
So, and then
these are from HST. They've been registered to Gaia.
So then there was quite an interesting thread going on, which you'll see about the 1/F being flagged as a snowball. And what threshold do you use for outlier rejection? Is it the standard 4?
Defaults,
Yeah. So there's some suggestions that maybe 6 or 8 might actually address that issue.
So I suspected that there was something there, so that's great. Thank you.
Yeah, sure. All right, next up.
All right. So thank you to the organizers for putting this together. I've already learned a lot about ways to currently improve my own pipeline, and I hope to give you all some food for thought as to possible implementations moving forward as well. So my name is Ryan Inslee. I'm a postdoc at UT Austin, and I got my PhD in Arizona a couple years ago. Whenever the first NearCam data came down, I worked pretty fervently over the first 2 days to try to get something together that could produce imaging mosaics that we could use for high-Z galaxy science. So I work primarily on reionization era galaxies, redshift 6 to 9 or so. And that's basically my background. So bit of a disclaimer here up front. I will say that Mick put a ton of effort into getting this great, I'd say, baseline approach to NearCam imaging reduction out to the community with their paper. I used that as a starting point, whenever that was released to improve my pipeline. But I have not looked at their code. Everything that I have done, I would say, is independent. I've tested things my own way. So while, I think that was a great starting point, and it was fantastic to have that. My hope here is that this independent approach that I'll be describing here to near-cam imaging reduction of deep blank fields effectively could help the general community. If you're interested, all of what I will show comes from JWST pipeline version 1.11.3 and the 1126p map. I tested some things against the most recent JWST pipeline version, and I don't see significant changes. But it's a fast-moving, dynamic thing right now, and I'll keep testing things as they move forward. All right, so outline, here's the things that I'll be discussing. So snowball fogging and masking, scatter light subtraction. I'm now learning that what I'm calling scattered light might actually be persistence. We'll get to that. Whatever F noise, 2D background, and bad pixel masking, outlier masking, whatever you want to call it. And I'll close with some considerations for future enhancements at the end of my talk. By no means am I saying that anything that I'm doing is unique. But again, I'm just hoping to provide some kind of complementary approach that we can all discuss together. So let's get on to snowball, fogging, and masking. Really all I'm doing here is just demonstrating the utility and effectiveness of my code. So for those of you on the front row or online, hopefully you can see, can't see the mouse, there it is. There's all these little snowballs in this, this frame from Sears. And then here's what happens after I apply my script. Again, largely based off of what Mick had mentioned in their paper. Here's another example. So not only works on small snowballs, but also large footprint ones as well, which is right around here. So here's effectively what my code does. For the fairly large snowballs, those are the ones that survive a median filtering of 7-pixel radius. I think it's the same thing as what Mick did. And then grow the footprint via binary dilation that depends on the size of the snowball that was being flagged. And then I also do a smaller snowball that has slightly different parameters on how you grow that footprint. And this was all just based on visual inspection on trying to tweak it by myself. But this is how I ended up doing things. I also carry forward the jump flagging of saturated pixels within snowballs to the next group. I found that helps mitigate some undesired features in the final mosaic. So scatter light or persistence, perhaps, subtraction. So I know that there are community tool sets already out there that deal with these kinds of things in F150, F200, but I've also noticed them as well in, for example, F090 and F115. And for the purpose of high redshift galaxy science, whenever you're trying to find high redshift dropouts, these shorter wavelength bands matter a lot. So for my kind of science, this was very important to me, so I invested time in trying to remove these features from these shorter wavelength bands as well. So here you can just see one example where I think, this is a Sears image. Ben showed something that had a very similar footprint from Jade's. But I constructed a template, and I'll tell you how I did that here in a second, that kind of subtracts this off. So you can see this kind of triangular feature-ish here, and then also this patch of enhanced counts over here. And this is what happens after I subtract that off. Yeah. So how do I do this? I construct a stacked 20th percentile data array from deep public imaging. So specifically, this is all exposures that have greater than 20-minute total time, exposure time on the sky. And whenever I do that, I get something that looks like this leftmost plot over here. So you can clearly see this pattern from whatever origin. I'm going to be agnostic about it moving forward, but all I know is that I don't want that in my final mosaic, so I want to subtract that off. So stack it all, and then create some way of basically determining the footprint of this feature that I want to remove. And this is what I'm just going to call the first stage of scatter light persistence template. All right, so I subtract that off first, and then sometimes there can be a residual, as you were able to see here. This elevated counts over here still remains. I want to remove that as well, so I do a second iteration of creating a template. From the images that I get after I do all this, and then I subtract that off. I get this template now, and I subtract that off, and you can see that that further improves the final image that I want to work with at the end of the day. I found that this kind of linear combination approach of iteratively creating new templates for different regions of the detector works pretty well. Happy to chat with people about this moving forward. Again, this is all just kind of done as I'm interested in the science. So there may be ways of improving this, but I do find that this works well at removing these features in general in all exposures of deep extragalactic data sets. So I'm hoping that it also applies to everything. All right, so 1/f subtraction, we've already discussed this. I don't think, again, that I have much unique to say. Just, I iteratively mask objects in the image before we're doing the 1/f subtraction. As Mick said, I do it amplifier by amplifier on a row basis first, and then subtract along the column. And this is what that process looks like. So you're seeing the image pre 1/f there, after I do the rows, and then after I do the columns. Again, I don't think I'm doing anything particularly unique here, just wanted to highlight that. So after the 1/f, this is on cal images, I should say. Then I do the 2D background subtraction. Something you might notice here, so this is the cal frame, and then this is it after I mask all the objects again iteratively with different footprints, different sizes depending on the signal to noise of a given object. You might notice that there's kind of this under subtraction region here. I think this might be the same region that Mick was showing earlier, actually. This is a Sears frame. So, this kind of instance where doing the amplifier by amplifier 1/f subtraction results in this kind of effect. So what I then decided to do was compute the 2D background for each frame on an amplifier by amplifier basis, and that allows me to then effectively remove this kind of undesired pattern where instances where you have a bright star in the middle of your amplifier. So again, iteratively mask pixels where the 2D, sorry, let me back up. So create a 2D background for each amplifier, said that. What I'm going to do, and I'll show this process as I move forward, is I first create a 2D background for a given amplifier. That's using source extractor Python, the set package. I iteratively mask pixels where the 2D background is too high. So, if there's a bright extended object or a bright star, this package will say your background is really high around that, but that's maybe not really the case. So if there is an outlier region in the background, I mask that, then recompute the 2D background array. I do this 2 times, and then any remaining outliers pixels are just assigned the background of the nearest non-masked pixel. So let me just show you what that looks like. So here, iterating through and then masking things for each amplifier. And then at the final step, any masked pixel is just assigned the background value of the nearest non-masked pixel. And that's why you sometimes get this kind of diamond shape pattern. That's just from the nearest non-masked effect. I can show that one more time because I think I have time. And what you'll see here once it gets to the third amplifier is that it is identifying right here this region where the background is too low in the original image, so it will correct for that. It does pick up some elevated background around the star, but overall it's, I'm doing the best I can at the moment. But I think this approach on doing the 2D background amplifier by amplifier, I'm hoping this could be a tractable approach to applying this moving forward for all data sets. So you can see here the before and after, over subtracted background here and then corrected for that, and I think it looks a lot better. So you can see there's also this region of enhanced background over here, and then that gets corrected. Maybe a bit hard to see on the screen. Apologies for that. All right, final thing that I'll mention with regard to steps that I've implemented so far is bad pixel or outlier masking. So I've been made aware already this morning that perhaps a lot of this is due to persistence from snowball hits in previous exposures. It's great to know, and I think there might be approaches to utilizing that moving forward. But even then, if you're the first exposure in your your set of exposures. I don't know if you want to then go and re-download all data set that came from before that. So this might be a way to address that in the first exposure of a given set of data. So here's an example of one of these hits. So here's the psi image on the left, the DQ array on the middle, and then the Poisson variance array on the right. You can see this clear outlier here. These 2 pixels are already being masked by the DQ array as do not use. But then a lot of these other pixels that have clearly elevated counts are not being assigned any data quality flag. These white pixels are all 0. But again, you can still see it in the Poisson variance as well. So the way my code works is that I identify these bad pixels by doing median filtered values in the Poisson variance, and then basically just saying, is the difference in the median filtered value versus the actual value of that Poisson variance very different by a factor of 5, factor of 10, depending on various footprints. You know, you can see me for details, but I've just kind of iterated my way through finding some kind of algorithm that seems to work fairly well. Still validating this approach, one of the concerns that I had whenever I first developed this was that it was also masking out the centers of bright but not saturated stars. So I developed a routine that seems to correct that and not mask the centers of bright stars, but again, requires further validation. The main reason I implemented this was because I was trying to reduce the Cosmos Web dataset. And there are certain regions of the sky that only have 2 exposures, and so the outlier detection step in stage 3 doesn't really do anything because there's not enough information there to flag outliers. And I didn't want these outliers to flood my source catalog. So that's that's why I did all this work. But I hope that this might be useful to some people moving forward as well. Happy to chat if you are interested. So here's just showing my final mosaic in F115W and Sears. You know, in the bottom right, you can see a region around an extremely bright star, binary, I think. And then here in the top right, this is the region with the poorest quality in my final mosaic. And I think overall it looks pretty good. There's still some regions of, you know, the background doesn't look fantastic. But I think it's still a lot better than what we were dealing with, you know, the first week of data, science data being delivered. So happy to chat about any of this. Just want to highlight here again, I need further validation of the bad pixel masking, outlier detection, whatever you want to call it. And then I've also been thinking a lot about astrometric alignment. One of the things that I noticed even just a couple months ago is that whenever I try to align both module A and module B data simultaneously, in stage 3, that is, that yields far poorer astrometric alignment than whenever I run all the module A data through stage 3 and all the module B data through stage 3 and then add everything together at the end. I don't know if others have had this experience or if there are, you know, solutions that people might have that are simpler than what I've done. And yeah, I would also like to say that it would be nice to have the option of outputting information on the WCS alignment that comes through stage 3, because sometimes it will just say like, warning, not enough objects, so alignment failed. But it would be nice to have that information tucked away somewhere or output to a file. I mean, I figured out a way to effectively log that information and store it into a file, but if there could be a approach implemented directly into the pipeline for that, I think that would be great, because I'd like to know where I need to maybe iteratively improve my source catalog for the input to make sure everything is working out well. So I think that's all I have to say. Thank you.
Continue typing my comments and questions. Let's see, thank you very much. There was some discussion going on. You'll notice it not directly related to your talk, but coming up again about slow direction stripes in the detector. And I think a lot of us are in the building here are a little surprised that that's such an obvious effect on the near-infrared detector. So continue that discussion online. Can you explain what happens with the bad pixel masking for bright stars? I mean, is that an issue?
Right, so it was an issue, and again, I'm still working on validating this, but so yes, my code was originally masking out the centers of bright but not saturated stars. What I have done now is told the algorithm that if there are a large number of pixels that it is flagging in the circular region, and the median counts in that region is a factor of X higher than that and like a median filtered huge footprint around it, then that's a star. And that, again, further validation, but I've tested this on like 10 frames, and yes, every single time it is correctly identifying only stars and not masking out the pixels around them. Yeah. Thank you.
In a moment, yes, just a second.
So yeah, thanks. I just wanted to comment on your template that you call Wisp-like, called Wisp-like. It's a feature that we've been seeing for a while. It seems to be static in detector space. I can say that while for wisps and claws we have some understanding of the optical mechanism underlying them, this one puzzles us a little, and the first two we encountered in commissioning, we had all hands on deck and all telescope folks like modeling things and helping us understand. This one, I think your empirical approach is really nice to deal with this. I just wanted to congratulate you on thinking about doing it this way, but we don't have yet an understanding of what that type of feature on this side of the detector is. So,
Okay, thank you.
Yeah, you also got kudos for your 4 bi-amplifier 2D background as well in the Slack chat.
Thanks.
Okie dokie. Hello everyone, my name is Armin Rest, and I will talk today about an alignment tool, JHAT, that we developed during commissioning. Of course, it has been a real team effort with many people contributing. We have, it's available on GitHub. We also have a read to docs page, and you can also install it with pip. So just to give a little bit of a background, WCS alignment is not trivial. There are issues because, for example, in some of the extragalactic fields, we don't have many Gaia stars, and of course Gaia is the best reference catalog. Sometimes we have HST reference catalogs for mirror images. Imaging has much less objects than HST. So there are many problems that you have to overcome to get a good alignment. And in my experience, each data set needs a somewhat customized approach. It's really difficult to have something that fits all. And so it's difficult to completely automate, but our goal was to do a tool that is flexible enough and nimble enough that you can actually adjust it to all of these different scenarios. So what we were doing is we get the level 2 outputs, a cal file, then we run JHAT, which does the alignment, and then you can just continue running level 3 on it as in the same way than with the original images. The one thing that is important is that after you have aligned them with JHAT, you have to skip the tweak reg step that does another WCS alignment, because that can mess it up. But that's an important thing before you do mosaics. So I want to show you a little bit what the NIRCam algorithm is to do that. It is not beautiful, but it works really well, and it's very robust, and that's one of the keys. So what are we doing? First of all, we find objects in the image, then we convert X and Y of these objects into raw DEC with the existing WCS. we do hierarchical matching using the AstroPy routine to match these object RADX with the reference catalog. And then after we have these matches, we convert the reference right essential declinaten into XY, again, using the existing WCS. So now we have a DX and a DY, which is just the X of the catalog minus the X of the object. So what we want to do is we want to identify this locus here. And we cannot even see here on this plot because it actually is, I think it's minus 30, so it's outside. So the most important thing is to identify these good matches, and then we can pass these good matches to TweakWedge to get actually the alignment. All of the work is right down here. So how do we do this? So we want to find these matches here. What we're doing is we take these dx values and we just rotate them with a slope. And so you can see here, just for examples, the red one is the original dx, and then we basically go through different slopes and adjust it. And for each of these different slopes or rotations, we make a histogram and then we smooth it out with a Gaussian. And then we get the peak value of this, which is associated to a certain dx. So then we plot these peak values versus the slope, and you can see it has a beautiful peak here. So we identify this peak, and then we can also get the dx value that is associated with that. So this gives us a first idea what kind of rotation do we have and what kind of offset in dx. So now we want to do the same with dy, but before we do it in dy, you can now take this estimate of dx and the slope and say like, hey, all of that stuff above and below is just a very rough cut. We kick out. So now we do the same with dy, but with this, the input is only the matches that pass a dx cut. And you can see now already it's much more cleaned up. You go through the same method, you rotate your dy, you look at the histogram, and what you get is you have these two cuts, and what is basically left is here and here. With that, you can make a very quick 3 sigma cut, and you have a very, very clean set of matches. So this here is JHAT produces then summary plots after it has found these matches. And so here you see one of these summary plots is before you align it. So here you can see dx versus y, dy versus x, and then some variation of that as well, dx versus y and dx versus x. So here you can see the rotation, and then here, of course, it is smeared out. So for helping to identify if this actually is a good solution or not, you have some control plots here on the right side. Up here, it's just y versus x of all objects. Then here, you have the magnitude of the objects versus the sharpness. So you can see that for a given filter, the sharpness is actually very well defined. So, for example, with JHAT, you can now also do cuts on the sharpness. It does change with filter, so you cannot just like take one sharpness cut, but for one filter, you can come up with a very good cut. The gray colors are objects that are cut out right from the beginning and with the initial cut. For example, I have a magnitude cut here because I know I'm using Gaia, so I do not expect to have any matches with stars that are fainter than 22nd or 21st.5. And the red, all of the red ones are the objects that are removed by this histogram cut that I just like described before, and the blue ones are the ones that are identified as the good matches. Here I just plot the magnitude of the objects from the JWST image versus the Gaia magnitude. You can see there's a nice relation. And so when you take the difference between these two magnitudes, you have a color-color plot if you plot it versus the Gaia color. So you can see you have these two populations with the same colors. I'm not a stellar person, but I think it's like different regions of the HR diagram that we have here. And this here is a last plot that is like kind of like useful. It shows you the roundness versus sharpness. And again, if you want to improve things, you can just make cuts here that already cuts out lots of the stuff that is not so good. In this example, it's a LMC. You have a lot of stars. It's pretty easy to do it here, but it's really good to demonstrate how this works. So when you have a sparse field, you can actually use all of these things to make it possible to align images that only have like 10 or 8 objects that are actually real for the alignment. So, and this is after the alignment. So if you go back and forth, you can see it actually works really well. So this is minus 0.5 to 0.5 pixels. So the spread here is well below 0.1 pixels, which is actually pretty good. So now I want to show you a different example. And I think that illustrates a lot of the issues and what the solutions are. So this is a mirror image. And as you probably know, mirror images don't have many objects. As redder you go, as more difficult it is to actually find matches and to align them. And I don't know which field it was, but there's a beautiful HST catalog for this field. And I was like, fantastic, I'm just using the HST catalog and everything should be good. And so I'm running it, and in my first image, I see this. There's no stellar locus, nothing. I was like, things are not working. So I overplotted the HST catalog on the mirror images. So the red and the cyan are both from this HST catalog. And I was like, wow, what's going on? These are all real objects. They're just like in the optical in HST. And the vast majority of them we don't have in MIRI. And so if you look closely, and I helped a little bit by indicating the cyan ones, the offset is plus 10 pixels in Y and about minus 2.5 pixel in X. So what can you do? I have an option in JHAT where you can say, hey, just like add a Y shift of that. So just to test it, I added the Y shift of 8. So now when you look at this, at the plot, you can actually start to see this locus. So at least now we start to identify the correct matches. So what you can do is you run through JHAT, it identifies these objects here. Here's like the output plot, and you can see it works pretty well. And it does find 28 good matches. But now, if you go back, so now imagine when you have this hierarchical matching and you're that far off, a lot of times, even if you shift by 8, this catalog is so dense, a lot of times you still end up with different objects. So you're not using all the objects that you can use. So in JHAT, we also have an option that says, okay, after you have done this first iteration, take whatever offsets you have determined from this iteration, apply this, and then redo it. So if you compare this one here with this one here, you can see many more objects are actually matched that are good. So this means that, with this one iteration, you can go from 24 objects to 57 objects. So it identifies all of these objects here and then finds the correct fit. So as I said before, it's just important that you have a look at the data and think about what are the special things about your data, how does your reference catalog compare in depth and density to your image, and then you can make decisions on how to proceed. So just as a summary, what can JHAT do? We have now implemented it for both JWST, all of the images, as well as HST, most of the image modes, and Mike Engesser and Justin Pierrel were the main authors for applying it or like modifying it for HST. We're pretty flexible with reference catalogs. You can use Gaia through an IPA. You can have custom catalogs of different things. So you can do already really, it has a lot of flexibility. Not all the flexibility we want yet. For example, you cannot pass your custom XY catalog. That's one of the things that we want to do next. But you have full flexibility. You choose your reference catalog, you choose your XY, you can use PSF photometry, you can use whatever you want, and say like, okay, these are my two catalogs, match them and give me the good matches. That's basically what JHAT is, this engine. We do have a batch mode, so we can run a whole set of images, and it is pretty flexible. You can adjust things for different data sets. We did write it during commissioning, and it was pretty crazy during that time. So we didn't pay too much attention to make this the most beautiful code. We have cleaned it up some. We still plan to have one more round of actually taking a step back, ripping out the core of it, just the matching, and then modularly add the different instruments on top of that. That will still take a little bit of time. The reads docs are kind of okay. I mean, we have some examples. There's still some more room for improvement, especially all of these options that I know, Justin knows, and some of the other people know. But I think it's really important to write down what you actually can do with them. I only showed you a small fraction of the options. We also want to have a config file to make it more transparent and more easily adjustable for different data sets. One of the things that we really want to do is to add uncertainties, because then you can actually mix a ground-based reference catalog and Gaia catalog. And that's especially good for extragalactic fields without any Hubble images a priori, because the ground-based observations will give you kind of like the skeleton to make sure you fall into the right minimum. And then with Gaia, you can get the final solution. We are also working very hard on the distortion terms. We will have them very soon. We just have to tie up a few ends and then run it on all the data, and then we will submit it and make it available to everyone. The distortion terms will be better. For most of the detectors and filters, the current distortion terms are already pretty good, but there are some filters where we have a trend. It's kind of like a pixel scale change that we didn't fully take into account. So there are things that will be improved with new distortion terms. So, keep an eye on that. If you have any questions, let me know, or Justin Pierrel also is very knowledgeable about JHAT. And just use it. We have a BIP tech entry, so if you use it, please cite us. It's always nice to get the credit for that. And let us know if you have any question. And I stop here. Thank you.
Excellent, thank you. There are a couple questions we'll chat while the poster folks start lining up. I was starting to get a little worried that we had 4 talks before lunch and it's getting late, but they're poster talks. Yes. I was relieved. JHAT seems to have a lot of overlap with Drizzle Pack functionality. As someone who's not an expert in either, can you explain the difference between what Drizzle Pack does and JHAT?
I think Drizzle Pack is like TweakWedge, or like the package around TweakWedge. So TweakWedge has similar functionality in some respect. It is less transparent, so all of this code is in Python. You can change it. It has more flexibility with the options. And I think the algorithm that finds the stars the good matches, I think, works more robustly than with TweakReg in our experience. So yes, there's overlap. I also hope that at some point we can put this into the generic pipeline. There's still a little bit of work to do, but yeah.
Yeah, I resisted typing in that question because it is a tool, not an automatic thing. But then when you said there's a batch mode, I was like, well, why would you have a batch mode if it doesn't work a large fraction of the time? So
No, you set it up for one data set, and then you can just let it rip for several hundred of images and it works. It's only if you go, one data set is MIRI, long wavelengths, and the other one is near cam, short exposures, then you have to do some adjustment. But for a given data set, I have run it on hundreds of images without an issue.
good, perfect, thank you.
Thank you.
There is an interesting long discussion about where the offsets come from, but it's going to be handled in
Yes.
Slack. And I added you to Slack so you can answer.
Okay.
Clicking over. Remember, this is your. You have to put just a slide, right? Okay.
Hi, my name is Savannah Gramsci. I'm from the University of Florida, and my poster is on JWST TweakReg, trying to fix frame misalignment. So this is kind of a common issue that we see in, pretty often in fields where there is a lot of like a very high stellar density, and it causes this sort of double star effect in products from stage 3 of the pipeline, but it originates from frames not being aligned properly in TweakReg. We see this problem happening in, for instance, Westerland 1, in the BRIC and Estridge Cloud C, which are both in the Galactic Center. And this issue is related to a lot of different issues that are on the pipeline caveats page as well. So some possible causes that have been brought up are that is that it's guiding on different stars between visits, that the frames aren't overlapping, and also that there might be a fundamental issue with the calibrations of the software. Some possible solutions that we tried were to try and tweak some of the TweakReg parameters, such as the fit geometry, separation, and tolerance. We also tried using JHAT, and the solution that we finally settled on was using a TweakReg helper function called JWST. So how you use that is that you basically measure the separation between the pixel coordinates of a star, use the calibrated image WCS, and then find the difference between what the actual cataloged position of the star is. Take that difference, and then you put it into adjust WCS, and it will shift over the WCS of the frame so that you can put it into TweakReg, and it'll use that better solution to align the frames together to then process them in stage 3 of the pipeline. Thank you.
Yeah, I think we're just going to do the questions online.
Okay.
But I will steal your microphone.
Is it better if I stand here? Yeah.
All right. Hi, everyone. I'm Varun Bajaj. I'm a senior staff scientist here at Space Telescope on the WFC3 team. But today I'm here to tell you about work I've done for part of the JWST FEAST program to improve the background matching and alignment for both NIRCam and MIRI. So there's kind of two halves to this, and we've heard some stuff about this already. So I'll start with the background matching first. And this is really more about MIRI, where we've seen people already talk about how the background matching in the pipeline as it exists right now kind of leaves you with these offsets and residuals still in there that then show up as discontinuities. And while aesthetically the discontinuities show up, they can actually cause more issues than that depending on the strength of them, especially in the cases where you have a lot of extended emission. You can have then a lot of your actual flux being rejected during the outlier detection step because it can't actually compute an accurate median between the overlapping regions. And then you obviously get gradients and other things too, and that's what's kind of being shown in these top two panels. And so you can see what the current pipeline produces for an example mosaic of, I believe this RM51 data using the current pipeline and our method. And what our method does specifically is kind of what we've heard about already with the montage style projection into one frame and calculating these pixel-wise differences. So we call it a pixel sky mesh step class because it is a replacement of the JWST pipeline sky mesh step. And what it basically does is uses the existing pipeline tools to project all of your MIRI images or your NIRCam images onto the same pixel grid before computing the background offsets, and then does a per pixel difference between any overlapping images and computes robust statistics from that. And then optimizes the sky levels by doing just the same sort of linear algebra optimization across all the overlapping tiles. And when you do that, it removes a lot of the gradients you can see. It removes a lot of this noise that you're kind of seeing in this panel, like along the bottom edge here, because it's fixing that outlier detection. And it actually reduces the noise in the background as well. The one con from this is that it requires a bit more of an accurate alignment because you need stuff to be really well aligned in pixel space. So that brings me into part two of this poster, which is specifically talking about alignment. And as we've heard today already, JWST alignment is pretty hard, especially when you have multiple bands and you have tons of stars or really, crowded fields or anything like that. The main issue that comes from it is actually the fact that the pipeline by default is using a DAO star finder kind of algorithm. And that's really not the best when you have these undersampled PSFs like a lot of NIRCam data is and even some of the MIRI data believe. And it's these inaccurate centroids from the star finding algorithm that often leads to these misalignments that Savannah and others have just talked about. So what we've developed is a package called one-pass fitting with a one-pass FOAT class in it. And what that does is it fits WebPSF models to your data to get PSF fit positions and fluxes that are extremely precise compared to the default DAO find style positions. And when you do this, you can then pass those output PSF fit catalogs into the pipeline to use in the tweak reg step for alignment. And you often get really good alignments that way. And not only that, you can then take all those align catalogs and produce one master catalog, which then you can use as a reference for other bands. So like, let's say you have an HST image that you've aligned all of your F200 images to. Then you can derive the reference catalog from that 200 image to align all of the redder bands. And you can form this ladder of alignment steps that actually holds pretty well because the one thing you get from the PSF fitting is extremely precise centroids. And down there at the note, I say what kind of the limits are, and this is a best case scenario, so, and on an average case, it's probably not quite this good, but these are standard deviations that you can get for flux and position. So the standard deviation of the flux is about 1%, 1.5%. And the standard deviation of the pixel positions after you project everything into the same frame after alignment is about 0.02 of a pixel or even less. So if you're doing NIRCam shortwave data, that's half a milliarcsecond. And when you have tolerances that tight, you can actually do alignment a lot easier because there's far less false positives and far less misalignment. And at the bottom here are 2 QR codes to the repos where the code and the documentation and notebooks will live later today because they're not done quite yet. But if you check later, yeah, I will have example notebooks and, more cases available for this. Thanks.
So I said no questions, but you have to answer the questions in Slack.
All right, so hello everyone. My name's Meredith Durbin. I'm a postdoc at UC Berkeley, and I am here to give a happy example of something in the pipeline that did actually just work out of the box when we weren't sure that it would. So I've been looking at doing time series analysis on non-TSO data. For example, when you have crowded stellar fields, the TSO option doesn't allow for dithering, but you want dithering in crowded fields to optimize PSF sampling. And so you might have short period variables in those fields that you want light curves of. So it turns out that the functionality to do this is already there in the pipeline, and it works. And so I'm just presenting a very simple recipe for how to do this, and showing some demonstration light curves of some RLI variables in ERS observations of WLM. And I really want to go to lunch, so I will stop there. Thank you.
Well, I want to thank you for giving me extra time for my end of session announcements. No, we do want to go to lunch. So I have 3 things I want to say before we break for lunch. One is there's a schedule shift after lunch. It's been updated online, but the talk on NS Clean is shifting down to the end of the session, and we will not be broadcasting it for bureaucracy reasons. Next, there's a couple tables that you may have seen out there on the left side in the cafeteria. One of them is got some folks that provided this new JWST search interface that was announced in the last week or so. It's still the rough edges are being smoothed out. I mean, it looks beautiful. I've used it, but they would just love for you to sit down and be a test subject for them and provide feedback. So please do that if you have some time. There's another table which has the Viz tools. It's a tool suite that we're working on to do certain basic operations. Same thing, that's a long-term endeavor, and so your input would be super valuable there. And then the last thing is, please don't eat somebody else's lunch. There's exactly the number of lunches as people who have paid for in-person registration. So that's it. See you all back here at 1:50. Recharge your batteries.